We can compute numerical solutions of differential equation systems in R. We refer to these systems as ordinary differential equations, ODE systems, and we would need to make sure that R has the package DE-solve in place, installed. That means we would have to download this package from CRAN, and once it is installed, you only have to install it once. We'll have to make sure that the script or the session we're running on R has this command, library de-solve. Let's take a look at how we install de-solve. Again, I want to remind you that I'm running RStudio on Mac OS X, and if you're running this in Windows or Linux, then the display will be a little bit different. In this version of Mac, I would go under this, in the menu, I would go to this option, Tools, and then I would select Install Packages. Okay, so we would like to make sure that we have the package that contains all the solvers for ODEs. So under the RStudio menu, is the menu bar, I go to Tools and I select Install Packages. Once I select that, this is what it looks like in my version here. And in this bar, I would type the name of the package that I'm looking for. In this case is de-solve. Then I would click install, and then I would be ready to go. I would expect that whether you run this in Windows or Linux, this process will be very, very similar. Let's compute numerical solutions for this system of ordinary differential equations. Here the state variables are u and v, and the parameters are a, b, c, and d. An important thing to note is that we're going to make an equivalence. We're going to stack or store the state variables into a vector. Think of the state variables as a state variable vector. So we're going to think of u and v as a vector x. We also have to be clear that what we have in these two equations, in these two differential equations, what we have here are the mathematical expressions. This is the formal way of assigning symbols to this mathematical model. When we code in R, we write a small computer program script. We will be using a notation that is typical of R coding or R programming. Okay, so there is a distinction between the mathematical notation and the variables in R. So we will write a code, and instead of using u and v, we're going to use x1 for u and x2 for v, and we're going to think of u comma v as a vector x. You'll see that it will become more clear in just a minute when we execute the ODE solver. So we type a function, we create a function in R. This function contains the right side of the mathematical expressions. Here these ODEs have a name because of when they were discovered, so this is typically referred as the toggle model. We have the function declaration. There are three input parameters of this function, t, x, and a parameter vector called parameters. Okay, so the important thing is here where we have expressions for the differential, for the ODEs, differential equations. It's important to keep in mind that when we define a function that has the ODE system, there are three main features. The inputs of this function are always, it's better to be consistent and always keep this format. There are three inputs, t, x, and a vector that stores the parameters. In this case, t doesn't appear on the equations, but it doesn't matter. It is useful to pass the parameters as one vector. In this case, is the last argument. This vector is storing the parameter values of the differential equations. And the last point to make is that the output of this function is a list, and this is a list that basically is storing the expressions or the values of the right-hand side of the equations on the ODE system. So we're gonna select this code and we're gonna run this code so that it stays in memory what this function is. Okay, and now we're gonna proceed. Once we have to select, oh, and a couple of comments here. On the top, we are making use of the library dsolve, and you will see after we compute the numerical solution that we're gonna plot those solutions. So the next step is to invoke the solver. The solver we will use is called LSODA, LSODA. Okay, so that command is here. LSODA is one of the best solvers of differential equations available in R. LSODA has several arguments that we have to specify. For example, the first argument is the initial values for x1 and x2. Remember, the state variables now are the state variables are stored in the vector x. That vector has two entries, and we have to specify what are the initial values. These are solutions of functions of time, so we need to also specify what is the time horizon, the time window. We want this to be computed for times starting at 0, ending at 50, and we want to take steps of 0.2 between 0 and 50. We also have to specify the name of the function that stores the equations for which we will compute numerical solutions. And in this case, this model has 4 parameters, so we are passing these values. A is equal to 3, b is equal to 2, p equals 3, and 2 is the value that we are passing for d. One more thing I should mention is that when we define this function, I did mention that the output of this function is this variable, in this case called ODE vec for vector. Since in this example we have two differential equations, then this variable is a vector with two entries. Originally, when this variable is created, we create that variable as a vector of zeros. So if we had an ODE system with 5 equations or 10 equations, we would create a vector of zeros that would have as many zeros as equations. So with 5 equations, we would need to have here a number 5. With 10 equations, we would have a number 10, and then we would have an expression for every single of those equations. Okay, so it seems we're ready to hit enter here. This would run LSODA, but LSODA is going to give us an output. So we're going to call this output maybe something like num sol1 or something like that, and then we hit enter. Okay, so this has executed. Maybe it was a little too fast, but it executed. This numsol1, let's see what that is. This is going to be a matrix. We can say dim of numsol1, and this tells us that this matrix has 251 rows and 3 columns. Okay, and if we now type here on the console the name of that variable, then we can see the values stored in that matrix. This is really this is quite something. So the first column stores the values of time. Remember, we're working with a time window starting at 0 and ending at 50 and taking steps of 0.2. So here's the first value, 0.0, 0.2, 0.4, and so on. And then the second column is storing the numerical values for u of t, and the last column stores the numerical values for v of t. Or the second column stores numerical values for x1 of t, and the last one stores the numerical values for x2 of t. Okay, so this is good stuff, a lot of numbers in that matrix, but perhaps one of the best ways to appreciate this is by looking at the numerical solution into a figure. So we use this command matplot, okay, and we want to plot here the first column of that output variable against columns 2 and 3. So we're going to say column 1 and here column 2 and 3. Okay, if I could just hit enter right now, and we would get a plot. Let's see if we can see this plot here. This is what it looks like. I'm trying to get this into the right dimensions here. Okay, so but we can make this plot a little better. So there are options here. We can specify, for example, we say type L, then that helps with the resolution there, and also we can use labels. I'm using the upward arrow, upward and downward arrows in the keyboard to go back to the previous line in the R console, right? So I would like to label, I'm gonna have an X label, okay? X label, we're gonna say here time T, and then Y label, we're going to say here u comma v, or you can say u of t, v of t. And I hit enter, and you can see how the x label appears here in the x-axis, the horizontal axis, and whatever I specify there for the y label appears on the vertical axis. Here's another example that contains an example of another system of ODEs with also two equations, but this example has a lot more parameters, has R1, K, A1, B, A2, and R2. So let's take a look at how we compute a numerical solution for this. So this is a script that is used to compute numerical solutions of these equations. These equations are called Rosen-Weig-MacArthur model, or Rosen-Weig-MacArthur equations. Okay, the top of the script is exactly the same we had before. We're invoking use of those packages. Then we have a section here in the script where we define the function that contains the equations. Now we have a lot more parameters. We still have two equations, so we still first create that vector of zeros, and then we're returning a list with that vector that contains the equations. Now instead of typing on the command line, we can specify initial conditions, the time window, and values of parameters, and then we can have a call to LSOTA. Okay, so let's run this code and see what we get as an output. So here we executed the code and we have a display of the numerical solutions. These are x1 of t versus and x2 of t. Now we are going to do something. We'd like to compute solutions if we change one of the parameter values, and we will do that in a very simple way. We'd like to compute solutions by changing one of the values of the parameters. The last parameter now will be explored as 650. We call this my parameters 2. We call LSOTA a second time, and let's look what happens when we run this. Now the solutions look completely different than they did before, and we can see these are still numerical solutions of x1 and x2. Now we conclude our conversation about using LSOTA to compute numerical solutions of ODEs.